noise my car makes up.
Okay, we're going to finish up section 2.1 first, and we're at the bottom of page 63 if you want to get there. We're doing example 6.
Boys and girls soccer go to the main camp. Boys and girls soccer team also to the main camp.
You'll have the video if you need it.
I will.
Okay. Example 6, rather than actually doing the graphing of this thing, we are going to just look at their graph because we've got to hurry. I'm sure that you could graph this if you needed to. The function that you're trying to find the limit of at a particular point is rational, which means you would scoop the numerator together in a set of parentheses over it and scoop the denominator in its own set of parentheses in order to graph it properly. So I'm assuming you can do that, and I'm assuming you understand the parenthesis concept. If you look at the graph of that thing, what they want to know is what's the limit as x approaches 2. So if you locate 2 on the x-axis in that picture you're looking at, you can see without them actually drawing it that there's an asymptote there, which you would expect because the denominator when x is 2 is division by 0, right? We say in this case that the limit does not exist, and you can use DNE, or does not exist. And the reason why is because, which we're going to discuss on the next page, the reason why it doesn't exist is because if you are on the graph, if you are pretending that you are a little gnat of some kind on the graph, if you are on the left side of 2, the left side of x equals 2, and you are on that graph, as you approach 2, you end up in the basement, right? You just go down and down and down and down. But if you are on the graph to the right of 2, and you are approaching 2 from the right, you go up and up and up and up. Which means that this graph or this function never settles on anything at 2. So it doesn't exist. There is no limit at 2. It doesn't exist. Okay? DNE. And then, of course, at the bottom of page 63, you see that we're leading right into this, what I was just talking about, approaching from the left and approaching from the right. These are 1- and 2-sided limits, and this is going to be lead to a very, very important definition. Luckily, it's not too hard to get. It's not very hard to understand. If you'll take a look at example 7, what you're looking at there is a step function, or a greatest integer function, we call it. By the way, if you want to graph an integer function, and you may wish to do that, you know where you find the absolute value in your calculator? Math, numbers menu. You will also find int x, which means integer x, in that as well. The same place. So if you go to your y equals screen, and you want to graph this integer function on your calculator, you go to y equals, and then you go to math, over to the numbers menu, and down there are ways at number 4 or 5 that you'll see int x. So you type that, and it will go back to your y equals, and it'll type int parenthesis, and you type an x and close it. And then when you hit graph, you get the step function. It's not quite as nice as this one because it's not zoomed in. But you can clearly see it's a step function. Okay? Now I want to talk to you about limits on the step function. First of all, can anybody tell me if you're looking at the graph, especially the one in the book, because it's a little bit bigger, what is the domain of the greatest integer function? All reals. Eventually, they're all hit. Where there's a hole is covered by a dot someplace else, right? Okay. What is the range of it? All integers, yeah. Just the whole numbers, positive and negative. Okay? Nothing in between exists for them for the range. So, if, for example, you wanted to know what is the limit as x approaches 3, your answer would be it does not exist. Because as you approach 3 from the left, you are on the step, which is at 2. So the limit as you approach 3 from the left is 2. The limit as you approach 3 from the right is 3. Now the value of the function at 3 is 3, but we don't care about that when we're talking about the limit. We don't care at all what the actual value is at 3. We don't care. But as you approach 3 from the left, you are constantly at the value 2. Do you agree? As you approach it, you get on the graph to the right of 3 and you come in from the right towards 3, you are constantly at a value of 3. So because the limit from the left and the limit from the right are not the same number, limit at 3 doesn't exist. That's what we say. You following me? Now, if you go back to, just to reiterate this, if you go back to the graphs on page 61 at the top, page 61 at the top, in all 3 of those graphs, the limit as we approach 1 is 2. Because from the left and from the right, you are arriving at 2, whether you come in from the left or the right. You don't arrive at 2 because there's a hole there in 2 of the cases, but you are arriving or getting closer to 2 from either side, so the limit is 2. You understand that? No? Yeah, you got that? Okay, go back to where we were then, and take a look at example 6. Oh, by the way, this is the notation. So in that step function, the way we would say this, to show that the limit doesn't exist and actually write it down and communicate with each other, we would say if y equals int x, that's the function we're considering. And by the way, you will see it written like this. These are the same thing. This is notation that's written rather than calculator. You can write it this way, I don't care. But in books where they just want to use notation that's customary, it looks like that. It's like a bracket with a fat sides to them. That means integer x as well, just so you understand the notation. And we would say this, if you're looking at the graph of that, we would say the limit as x approaches 3 from the left. It's in the exponent position, but it's just a symbol. That means from the negative side of 3, left of 3. Doesn't mean negative 3 or anything like that, or a negative exponent. It means to the left of 3. The limit as x comes into 3 from the left of y is 2. Do you understand this lingo, this way of writing it? Yes or no? Yeah. And then we would indicate this. We would say the limit as x approaches 3 from the right of 3, put a plus sign there, of y is 3. Therefore symbol. The limit as x approaches 3, not right or left, but just approaches 3 of y does not exist. Don't write equals here because you can't equal a something that doesn't exist, okay? But the limit of, as we approach 3 of the function doesn't exist because the limit from the left and the limit from the right are not equal. That's the conclusion we make. Y'all follow that? This is the way of writing those ideas. Okay, so look at example 8, please. This is a classic test question, even on the final exam, way out in the spring. They'll ask you questions about graphs, like the thing that's to the left of example 8, to see if you really, truly, conceptually understand the concept of a limit and the difference between that and the function value. So, in that graph that you're looking at in example 8, and I'm just going to ask you some things, not necessarily what they're asking. I just want you to look at that graph. We're just going to discuss it for a minute. Can you tell what is the limit as x approaches 2? 1. Good. What is f of 2?
2.
Don't understand these?
Yeah.
Are you sure you do, Jose?
Not really.
Look at the value, x equals 2. As you approach from the left, you are a height of 1, right? As you approach 2 from the right, you're coming down, but you're approaching 1. So the limit is 1. But the value at 2 is 2. See the dot above it?
Yeah. Okay.
So f of 1 is 2, but the limit as you approach 2 is 1. Catch that? Therefore, it is, we call it discontinuous at 2, because the function value and the limit are different. It's discontinuous there. What is the limit as x approaches 3?
2.
Would you agree? The limit as x approaches 3 is 2. What is f of 3?
2.
What do you conclude? It's continuous at 2. I'm sorry, it's a continuous at x equals 3. Because the limit and the value are the same. Now, what is the limit as x approaches 1?
There's none.
Does not exist, right? So you write DNE. Now, here's a tricky question. What is the limit as x approaches 4? The answer to that question is not D and E. It's because we don't know what's going on to the right of 4. There may be something going on. It may be continuous there. We can't tell. And so this is what you say. The limit as x approaches 4 of this function, we can't tell. But from the left, it is 1. So you qualify and give as much information about it as you can. You cannot conclude that the limit is 1. But you can conclude that the limit from the left is 1. And so you say what you know when it's at an endpoint. So what's the limit as x approaches 0?
As x goes to 0 from the right, it is 1.
Right. So when you say, what is the limit as x approaches 1? You say, I can't tell. But from the right, it is 1. You cannot tell what the limit is. Okay? Is it continuous at 1? It is, because from the information that we have, the function value and the limit that we can see has the same value, so we say it's continuous.
1 or 0.
What's that?
1 or 0.
1 or 0. 0, 0, 0. Sorry, 0. 0. I was thinking the value 1 when I said that. Sorry about that. Yeah. Okay, so the limit doesn't exist at 1, but from the left, if you wanted to say it, and you could say the reason it doesn't exist is because the limit from the left is 0 and the limit from the right is 1, therefore it doesn't exist. But when you ask, what's the limit as x approaches 0, you say, I can't tell, but from the right, it's 1. And it is continuous because f of 0 is 1. You know what I'm saying? If they ask about continuity, they won't. They just talk about limits today. We'll talk about continuity in greater detail later. Last thing. It's called the sandwich theorem. You can call it S period, T period. You don't have to write sandwich theorem if you don't want. It's an interesting theorem, and it's fairly obvious why they call it that when you see an example of it. It says this. If you know two functions, we'll call them G and H. I want you to look at the red functions at the top of page 65 there on the left. One of the red functions is G, one of the red functions is H, and F, which is blue, is always in between them. They are ugly looking functions. I don't even think you could come up with an equation for them. Maybe. They're nasty looking functions. But the one thing we see there is that the blue function is always sandwiched between the red ones, G and H. And if G and H ever have the same value, then surely the blue one must have that value at that, because it's sandwiched in between. You understand the concept? So this is what it's saying in theorem 4. If you think about that graph we just looked at, it says, if G is less than F is less than H. In other words, if F is in between G and H for all of the X's except C, then the limit as x approaches C of G is the same as the limit as x approaches C of H. If that's L, then that means that without knowing anything more about F, that is, as you approach C with function F, it's also L, because it's sandwiched in between. So if they ever have the same value, so does F in between. We don't know anything about any other locations except for at C. So again, this is calculus. Concept is fairly easy. Making it work can be rough. So this example 9 is an example of the sandwich function, or the sandwich theorem. What we wish to find is the limit as x approaches 0 of x squared sine of 1 over x as we approach 0. So we've got, this is going to show up, yep. So this is our function f. This is the one that we wish to trap in between a couple of functions. And you've got to come up with the two functions we're going to sandwich in between. So f of x is x squared sine 1 over x. That's our function, and we wish to know what is the limit of this function as x approaches 0. That's what we want to know. X approaches 0. What's the limit as x approaches 0? X squared sine 1 over x. Now, I hope you understand that you cannot directly substitute 0 for x because you'd be signing something that's undefinable. Does that make sense? Now watch, this is tricky. This very first thing is something you may never have considered before. What you do is you take, by the way, this usually almost always applies to trig functions, sine and cosine. When you try to prove something strange about sine and cosine, especially if substituting your limit behind the sine or cosine is impossible. It's a very limited theorem, but it's very useful in this case. What you do is you start out by making a statement of fact. The sine of 1 over x is always between negative 1 and 1. You think about that. It doesn't make any difference what sine is continuous everywhere, right? You don't ever have to pick up your pencil when you're drawing a sine curve. So it doesn't matter whether you're signing x or signing 1 over x. This is an angle. And the sine of any angle has a y to go with it. But unless you put an amplitude in front of the sine of some kind, no matter what this is, I don't care if it's 1 over x squared, I don't care if it's root x, I don't care what it is, you can always plug an x value in there and it will produce an angle that you can sine. And the sine of any angle is always between negative 1 and 1. Yeah? I'm going this way. You following me? This is a fact. You do not need to justify it. You do not need to explain it. You just need to state it. Anyone who studied trig and thinks about it will know that this is a good place to start because it's always true, no matter what this is back here. Okay? So we start out with this statement that is true, and the piece that's in between negative 1 and 1 is the trig function we're dealing with. What about that? Well, if you multiply everything by x squared, will these inequalities still hold? What could make these inequalities switch places, switch directions?
Negatives and positives.
Well, just negatives. If we were to multiply by a negative number, here, here, and here, that would make these signs switch directions. But what do you know about x squared? It's always positive. So we don't risk switching these signs by multiplying everything by x squared. In other words, I start out with the bare sine function, the bare trig function, trap it in between negative 1 and 1, and then I continue to build it up until the stuff inside looks like this. Constantly being true to the algebra and what might happen. So I'm going to multiply. I need this to be in front of that x squared. I need this to be what I'm looking for as a sandwich. Can you see the sandwiching going on already between negative 1 and 1? I am going to now multiply every single piece of this inequality by x squared. So I get this, and I get this. You follow that? So we built it up so that this can be there, and if I'm going to multiply the inside by x squared, I got to multiply the outside pieces of the sandwich, the bread, by the same thing, and I don't risk switching directions on these because the thing I'm multiplying is guaranteed to always be positive. Again, you don't have to justify any of that. Taking this and multiplying by x squared is going to yield this. Now, here comes the limiting part. This is why I'm approaching is 0. What is the limit as x approaches 0 of negative x squared? It's not hard. 0. Because of direct substitution, we can directly substitute it here, right? Over here on this side. What is the limit as x approaches 0 of positive x squared? 0. Since these have the same limit at 0, this must by the sandwich theorem. So you show me the limit from the left on the left side and the limit on the right side. They better be the same number because if they're not, this doesn't hold because if they have different values, you can't sandwich in between. Exactly the same value when x is 0, and that's where I wish to consider this, and I couldn't do it by direct substitution. But since that's always sandwiched in between, we say, therefore, the limit as x approaches 0 of x squared sine 1 over x equals 0 by the sandwich theorem. Did you follow that? If I had time, I would have you try one that's like this. You may want to come back to this video or take a picture of this or whatever, because that's the strategy for doing the sandwich theorem. You'll have to do it once or twice. And like I said, the sandwich theorem usually applies to functions involving sine and cosine of something that you can't evaluate by direct substitution. Sandwich theorem. Trap it in between something you know is true. If it's cosine, it's also between -1 and 1 to start. Then you take that true inequality and you do whatever's necessary to every piece of it until you get this in the middle. Then you evaluate the limits on the end. They better be the same number. Therefore, this one has to have that limit there as well. That's the idea. So get to apply that. All right. So now I have to move on to section 2.2. We got to get through this before the end of the day. Still talking about limits because that's the title. That's the whole thing about this chapter. The whole chapter is about limits. Okay. So
This one's a lot shorter.
what's that?
This one's a lot shorter.
Yeah. This is not hard. These are not hard concepts. A little bit hard to apply the algebra to sometimes, but not hard concepts. So now what we're going to do is investigate what happens this way, what our limits are going to look like. Instead of something like this, the limit as x approaches 3, either from the right or the left or something like that. We're not going to approach 3. We're going to approach way heck to the right or way to the left, and we say it's going to be positive or negative infinity. So our limits are going to look like this. We're going to say, what happens to this function we're looking at as x gets really big to the right or really big to the left? As x goes out, what value is the function approaching? That's what we're looking at, right at the beginning of this section anyway. So it's going to be important that you be able to use your calculator on this, and you're saying, how do I make it approach infinity? Well, you look at table values of x for x really large and see if you can see what it's saying. So consider the first example. It says we've got a function x over the square root of x squared plus 1. This is our function. Anybody that, without graphing it, does anybody have any idea what that looks like? You may not know exactly what it looks like, but can you consider the limit, for example, as x approaches infinity? Hurry back. Think about this. Think about what's happening in your head. Think about what's happening as x gets really, really, really big to the right.
Will it approach 0?
No.
And get smaller?
This is the kind of thinking you have to do. Consider this. This is the part that's probably the problem. I mean, that's obviously going to infinity, right? What's going on here? Well, if you consider what's happening to this function when x is a million, then what you have is a million over the square root of 1,000,001.
Squared.
No,
So
sorry. 1,000,000 squared plus 1. So what I'm saying is, the bigger you get, the less contributing this 1 is. It doesn't contribute much when x is really large. So let's pretend that it doesn't contribute anything.
So get closer to 1.
Yeah, because the square root of x is x, and you end up with x over x. Just getting closer and closer and closer to 1. As x gets really large, this becomes less and less significant, and we end up really looking at x over x, right? And so we say this is 1 by reasoning and analysis. We can also verify in the calculator in just a minute. Using the same sort of thinking, what is the limit as x approaches negative infinity?
We don't have to worry about negatives because it's squared, isn't it?
The bottom is, but the top isn't. Yeah, would be -1. Now, think about this. it's going to, we're talking about going way, way, way out to the right again. Will this thing be approaching 1 from above it or below it? In other words, will this number be more than 1 or a little tiny bit less than 1 as x gets large?
More, a little more, a little less.
Will this number be bigger or smaller than this one? This one will be smaller than this one because that 1 does contribute something, right? So it's going to be approaching it from below. Because this is always less than 1 a little bit, but it's getting closer and closer to 1, right? Will this approach it from above or below the negative 1? In other words, is this going to be between 0 and negative 1, or is it going to be slightly bigger than negative 1? When I say bigger, I mean below it.
It's going to be this one.
Yeah, it's going to be approaching it, coming in this way. So the graph, without ever seeing it, just analyzing what's happening as x gets large, is probably, the graph's going to be probably something like this. Over here is, by the way, when x is 0, you end up with 0 over 1, so it's going to hit here. And it's going to come up and approach this like this, and it's going to come down and approach this like that. Right? Now, it never actually arrives at 1 and negative 1, but those are still the limits. And because it's approaching a specific value as it goes farther and farther and farther out, we have a horizontal asymptote at these locations. That is the actual definition of a horizontal asymptote. If the limit of a function as x goes to infinity is a number, then y equals that number is a horizontal asymptote. Does that make any sense? That's its definition. The definition of a horizontal asymptote is if the limit as x approaches infinity of a function is a number, then y equals that number is a horizontal asymptote. So there are 2 of them in this one. Because as x goes way the heck to the left, it settles on a y value of negative 1. So negative 1 is also a horizontal asymptote for this graph. You follow? Now let's say that you had something more complex than this and it was really hard to tell what this thing was approaching. Let's use the same one and I'll show you how to use your calculator to determine that, what the value is, so that you can find a limit without actually having to do any algebra. Okay? So go to your y equals screen. We got to put something in there. Go to your y equals screen and put that function in there. Make sure you're using parentheses appropriately. So it would be x divided by, and then you could just use the square root symbol. It'll scoop it all together. X squared plus 1. Close it. Now, if you graph it on a standard screen, you'll see what I told you you'd see. It's not very exciting. But a standard screen is not a very good place to look for what it's going to settle on. Because going out to 10 and negative 10 is hardly going to infinity or negative infinity or getting close, right? And if you make your x's go way, way out there by adjusting your window, you're not going to be able to see any details very well. The way to check what's happening at infinity and negative infinity is better done with your table. It's more definitive. So I want you to go to this right here. Above the window key, you see table set. So go table set. And when it says table start, it means where do you want to start? I'd like to start at 100,000 because I want to go way the heck out there. And I want to increment it by thousands. That's the delta table. So I'm starting at 100,000 and then I'll be 101,000 and 102,000. That's what it's saying, is how it's going to increment. So now go second and the graph key, and you can see it has settled on 1 by then, which is what you expected. So if you want to know what happens as x goes way the heck to the left, go back to your table set and insert a negative sign. Now you're going way the heck to the left without really adjusting much. Go to your table and it has settled on negative 1 by then.
Does it actually settle on negative 1?
It never actually reaches it.
Okay.
But your calculator says it does because it has already gone beyond its decimal approximation that's 23 places long. So it is already 0.999999923 out. When it gets to the next 9 past the 23rd place, it just says that's negative 1. You need to understand as the operator of it and the understander of asymptotes, it doesn't actually ever arrive at 1 or negative 1. It just gets closer. And this has already arrived because it has a limited amount or ability to approximate decimals. Okay, enough of that. Look at example 2, sandwich theorem revisited. Boy, we came back to that in a hurry. This time we're not asked. Remember when we said we were talking about sine x over x, and we said if we approach 0, the value is 1. If we approach 0, we can't arrive at it. But if we approach 0, the limit is 1. Now we want to find that very same function and figure out what happens as x approaches infinity. So we're getting away from the origin. We're coming into infinity. So this is our function now, still sine x over x. But now we're asking not what happens at 0, which we can't directly substitute. We learned about that. We decided it would be 1. Now we're asking what happens to this function as we go way out there to the right. We'll do the left one in a minute. It's going to be a lot easier to think about once we've thought about going to the right. Think about this. What did we say that sine was always trapped in between?
-1 and 1, right?
-1 and 1. So this numerator is not going to get very big or very small. This denominator is going to get huge without restriction. What happens as you put something very small over something that continues to get larger and larger and larger? What is this approach? Gets closer to 0. That's just by thinking about it, right? However, it's going to alternate in sign as it gets closer to 0 because this thing sometimes it hovers between -1 and 1. So sometimes its value is negative and sometimes it's positive. So it's going to do this kind of a thing. As it goes farther and farther out, it's going to go like this. It's going to settle on 0. But it's not going to approach asymptotically like that. But still, by the definition of asymptote, we say that y equals 0 is an asymptote. Even though it doesn't move towards it like that from one direction. It goes above it, below it, above, below it. It gets farther, not as high above, not as high below, until it settles to where it's practically indistinguishable. You following? So, what happens as we go to negative infinity?
Probably the same thing.
Exactly the same thing, because again, this is going to alternate in sign, but differently than the way it did before, because we got an extra negative on here. This x has got a negative on it. But this is going to alternate between positive and negative, but not get very big. So it's going, like that. So it's going to come out like this and settle on. Here's how we investigate that in the calculator again. Go back to your y equals screen and type in, make sure you're in radian mode. Type in sine x. Make sure you close the parenthesis after the x on the sign. Divided by x. And take a look at your table set. It's just where we want it, only it's negative, so I'm going to delete that, so I'm going positive. And look at the table, and you go, that's not 0. Oh, yes, it is. Those are really, really tiny numbers and getting smaller. Notice that the signs keep changing on them, but we expected that. Nevertheless, the size of the numbers, the y values, are getting smaller and smaller and smaller. Now, if you want to check to see if it actually ever does settle on 0, what do? Go to your table set and set your starting value at 10 million instead of 10,000 or 100,000. Just to add 3 or 4 more zeros. And go to your table. Well, it hasn't settled on 0, but they're a lot smaller than they were. That's evidence that you're approaching 0. Okay, if you go back to your table set and just change the front number by inserting a negative, you can see that you get the same sort of thing. The numbers are getting smaller and smaller and smaller. Positive and negative, we don't care. But you may be thinking, well, what's that got to do with the sandwich theorem? Everything, watch. What we're going to do is we're going to start with this function's trig part. So we're going to say sine x, and we know that that's always trapped in between -1 and 1. That's where you always start. A fact. Then, how is this different from what I started out with? Well, we got to divide everything by x, right? So I have -1 over x, less than or equal to sine x over x, less than or equal to 1 over x. So we now have the function we wish to sandwich in the middle. So now we take the limits of the bread pieces. We take the limit as x approaches infinity. Well, infinity. It could be positive or negative. We could put plus or minus here and consider them both at once. of -1 over x, well, that's 0. Because a constant over something getting bigger and bigger and bigger and bigger is 0. You don't have to say why. You just have to understand that reasoning right there. And then over here on this side, the limit as x approaches positive or negative infinity of 1 over x is also 0, a constant or something that continues to get bigger. Therefore, the limit as x approaches positive or negative infinity of sine x over x is also 0 by the sandwich theorem. So we can use the sandwich theorem whenever we involve some embellishment of sine or cosine. Start with the sine or cosine, and then you just keep building up all pieces of the inequality until you have the actual function in the middle, and then you limit both ends, and they better limit at the same number with what x is approaching. Therefore, the middle must also. Yes?
Did you divide everything by x because the f of x was sine x over x?
Yes.
So if it was like 3 sine x, would you multiply everything by 3?
Yep. And if it was sine x over 4x, then you'd divide everything by 4x. Same thing would happen, just gets there faster. It's 4 times as big each time. Okay? So if you want to revisit the video and look at that again and think about it slower and pause and stuff, you can, but I'm moving on. Okay, look at theorem 5. Another set of properties. And again, even though we're approaching infinity instead of a particular number, properties still hold. If you're considering two functions, f and g, we're at the bottom of page 71 if you're watching the video. But this time we've got f and g, and this time we're going to approach positive and or negative infinity. If those things for f and for g settle on a value called L and M, then if you add f and g, that new function's limit at infinity is L plus M. And the subtraction is the subtraction of the limits. And the product is the product of the limits. And if you multiply one of the functions by a constant and take its limit, then the limit will be k times the limit it had when you didn't multiply by it. And so forth. Quotient rule, everything's great there. It's going to be L over M so long as M is not approaching 0. Not M approaching 0, but so long as the limit is not 0. And the power rule, if you take one of the functions and raise it to a power, then the limit of that new function as it approaches infinity is the old limit raised to the same power. It's exactly what you think it's going to be. And as you will see in just a moment, fairly useless. These properties. They can be useful in certain circumstances, but most of the time they are not. You're going to see why here in just a minute. So I want you to look at example 3. We've got the limit as we approach infinity of 5x plus sine x over x. And on all of these limits, it's really a good idea to think about what may happen as x gets large. Think about what the limit's going to be in a reasonable way, in a rational way, before you try to do anything algebraic, so you know what to expect. The limit as x approaches infinity, 5x plus sine x. Think about what happens as x gets really, really, really large. That sine x is always trapped between what?
-1 over 1.
So that sine x will either be positive or negative, but it won't be very big. Which means as x gets really, 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 really large, this value right here has less and less and less of a contributing factor. It doesn't contribute much. So feels to me like it's going to approach 5x over x, which is 5. Feels like the limit ought to be 5. But let's apply the properties that we just said. It said if we have a function f over a function g, and you consider each of them separately, then whatever this one's settling on over whatever this one's settling on should be the limit, 5. And so we consider this. We say, okay, so what is the limit as x approaches infinity of 5x plus sine x? Just that one. What's its limit? Anyone? Think about what's going on. This is not much of a contributor.
This is just infinity?
It's just infinity. Because this just keeps getting bigger 5 times faster than just if there weren't a 5 on it, right? It's getting out there. And so now that property that we were trying to use, which is this limit over this limit would be our answer, is already bogus because this doesn't have a limit. Neither does this. If you take the limit as x approaches infinity of x, it's also infinity. So what you end up with, according to the properties, is infinity over infinity, and yet we know this thing settles on 5. Yeah, what I mean is those properties are mostly useless. So finding the limit of this and finding the limit of this and putting one over the other does not tell us the limit.
So are properties always true?
They're always true, but not always useful. It's always true. But listen, the property says if the limit of the numerator settles on a number and the limit of the denominator settles on a number, then the limit of this one is this number over this one. But these are not numbers.
Right. Okay.
So the property doesn't apply. Still true, it just doesn't apply because it's not a number, L and M, which makes it useless. Right. Well, not always useless, but a lot of times, okay?
Basic.
So when that happens and you're trying to apply the properties, you go, well, that one's going to infinity, so it doesn't apply. Now what? Well, now you start using your skills for algebra to simplify this. In other words, we put 5x over x plus sine x over x and take these limits instead. This one cancels, leaving us with a 5 in that limit. And this one is something small over something huge and is 0. So I end up with 5 plus 0, which is 5. So I used the addition one, and that one actually worked because they did settle individually on something that were values that I could combine. And so we say the limit of the function as x approaches infinity of f of x, whatever that is, in this case is 5. But applying the quotient property failed because they didn't settle on anything. Applying the addition property after manipulating this a bit did work. Okay, so I want you to consider exploration 1 with me for a minute. Look at example, or the exploration 1 on page 72. Oh, example, the first part of it is the one we just considered. Look at the next one. It says let f of x equal sine x and g of x equal, sine squared x and g of x equal cosine squared x. The behavior of f and g as x approaches infinity. Separate. What does f, which is sine squared x, what does that settle on as x gets large? F is sine squared x, so let's write it up on the board. The first function, f of x, equals sine squared x. As x gets really, 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 really big, what does this function settle on? First of all, what does it look like? It does not look like this, because the values are always positive because you're squaring it. It looks like this, I think.
It looks like a normal sine wave shifted up.
No, not shifted up one.
Okay, just
What?
I know you can see it. It looks like that. It's like it's
Yeah, everything that was below it has been reflected up because it's all positive, right?
It's just smoother rather than like.
Yeah. Okay, so this thing, what is it, as x gets really, really large, taking a look at that graph, as x gets really, really, really big, what number is this settling on? It's not settling on anything. This limit, as x approaches infinity or negative infinity, because it behaves the same way to the left, of this function does not exist. It doesn't settle on anything. What about this one, g of x cosine squared x? What is it going to settle on?
Probably not.
It doesn't exist either.
Crazy.
So I can't apply the properties that I was thinking of to figure out what f of x plus g of x is. F of x plus g of x as a new function, you can't figure it by adding the two results because there's no result. However, you know what this limit is.
Why?
1. Because sine squared plus cosine squared in any instance is 1. Again, the properties were useless in adding them together, but we know what it is without thinking very hard about it. The limit of their sum, this limit here, as x approaches positive or negative infinity, is 1.
I thought the limit of the sums was the sum of the limits.
It is, but these limits don't exist, so how do you add things that don't exist?
You can't, so how do you get one?
By knowing this identity. So the properties didn't tell us this. Trigonometry told us this. So again, properties were useless in adding these two together because they are individual limits don't exist. So the property didn't apply here. Something else had to. Here it was algebraic simplification. Here it was knowing an identity. You see what I'm saying? So sometimes you have to resort to something else. That's all we're trying to say there. Okay? The same thing is going to happen with number 3 and number 4. I'm not sure I have time to visit those. Just look at part 4 with the discussion we've had so far. It says, based on parts 1 through 3, what advice might you give about applying theorem 5? It's really limited and pretty. That's the advice you give. It's not, it doesn't work for us. The properties are true, but only if the limits are numbers. And if they're not numbers or they don't exist, then they don't apply. You have to come up with something else. The moral of this story is, just because the property doesn't apply doesn't mean you don't have to continue. You still got to look for the limit somewhere else, some other way. Okay. Now I want to talk about what happens if the asymptotes are not. We were talking about the limit at infinity, and if it settles on a number that was an asymptote, horizontal, right? Do you remember us just talking about that? Sunny doesn't. She's looking at me like I'm crazy. But
She was here.
she wasn't.
She does. That's what she does.
Now, you know as well as I do that there's all kinds of asymptotes out there, but the ones we consider the most are horizontal and vertical ones. We have considered horizontal ones. We saw that with the very first function we looked at. Now I want to consider vertical ones. Okay? So, for just a few examples here, example 4 and 5, we're going to consider what vertical asymptotes do and how we can find them stuff and what their definition is. Let's see. Consider this, the function 1 over x. Do you all know what that looks like or not really? Do you have an idea what that looks like as a graph?
Right.
To the right of 0 it does.
Yeah.
It looks like, whoa. It looks like this. To the right. What does it look like to the left?
Probably
Down here in the third quadrant.
Yeah.
Down here in the third quadrant. So just as a reminder, and I know it's been a while since you haven't seen this for a while, but and this has nothing to do with the exercises. Just to ask you, is this function odd or even, or neither? Has origin symmetry, so it is
Even.
odd.
Oh.
Y-axis symmetry makes it even. Origin symmetry, which means this is reflected in these quadrants, makes it an odd function. That's neither here nor there. I just wanted to bring that, try to regurgitate that out of your memories. Okay. So, based on this then, now notice what I'm going to write here in this limit. The limit, I'm not going to infinity anymore because I don't care what happens as x is large. That tells me about horizontal asymptotes. What I want to know is, what's going on right here at 0? What weirdness is happening there? What happens as x approaches 0? First of all, it doesn't exist. Because from the left and the right, it's not the same, right? So what happens as we approach, what is the limit as x approaches 0 from the right side? What do the function values do? Where do they go?
They go up, go up.
How far?
Infinity.
To infinity. So we have limits that land at infinity. We've already seen it.
But it's like that.
But notice that my limits now are not approaching infinity. That's what we were doing with horizontals. Now we're approaching a number where something bizarre happens. An asymptote, a vertical one. What happens as the limit as x approaches 0 from the left side? What's its limit?
Negative.
Negative infinity. And so the limit doesn't exist. But if you wanted to go that far, therefore, the limit as x approaches 0, not with a plus or minus, but of that function 1 over x it's not equals either, it doesn't exist as it approaches 0. Okay, so that was
The
exciting,
limit doesn't exist.
Does not exist.
because the limit from the left and the right are not the same.
Negative and positive.
One goes down and one goes up.
But there's an asymptote there? Asymptote there?
Yes, and this is its definition. If you approach a number and the function goes to infinity or negative infinity, that is a vertical asymptote, and that's the definition of a vertical asymptote. If you are approaching the value of x where that asymptote, you suspect that asymptote occurs, then the limit from left or right, if it goes to infinity or negative infinity, is a vertical asymptote. And it doesn't matter whether it's only from one side or the other. For example, if I consider the function natural log of x, what's the limit as x approaches 0 from the right of this function? Think about logarithms. Do you know what log functions look like?
Negative infinity?
Negative infinity, because a logarithm, as you know, approaches the y-axis from here and goes out, right? And so we would say negative infinity here. What is the limit as x approaches 0 from the left of the log of x?
That one doesn't exist because you can't line negative.
Yeah,
You can't
it's
line
a DNE. It's even worse than a DNE. You would say, I guess you could write DNE, but you'd have to give an explanation. You might say because negative numbers are not in the domain of log. You can't consider it. So what I'm saying here, the only reason I brought this up is, still, y equals 0 is a vertical asymptote for this. Even though it approaches in one of the infinities only from one side, it's still a vertical asymptote. On the other side, it doesn't exist because there's no domain there.
Is it a limit then?
The limit as x approaches 0 from the right of log x is negative infinity. Therefore, y equals 0. This limit that we're approaching this time, not what it's equal to like before. This thing that we're approaching is a vertical asymptote. X equals 0 is a vertical asymptote because approaching it causes the function values to go to infinity of some kind.
So does that one have a limit?
This
Not
one?
the log of x, so that graph has a limit?
No, it does not.
So then what's a limit then?
If the y values approach the same value from left and right, it doesn't even exist from the left.
So it has to be a y value for it to be a limit?
The same y value. It has to be approaching the same y value for the limit at that number to exist.
All right.
Now we could say, since this doesn't even exist, this domain doesn't even have negatives in it, you could say on its domain, the limit is always negative infinity as it approaches 0.
Because that means it doesn't approach the left.
Right, so you would say, you'd have to qualify it. On the domain of this function, the limit as x approaches 0, not from the right or left, just as the limit as x approaches 0 on its domain is negative infinity. You could say that.
If you say on the domain, it just eliminates everything.
That's not the
That's
domain. Yeah, you don't even have to consider this. So there's only one limit to consider, and its value is negative infinity. So that is the limit as we approach 0. Okay? So that's a really ticklish qualifying one there. All right. Let's take a look at the next one. Oh, what about this one? F of x equals 1 over x squared. What does that look like? Anybody?
That'll approach you.
What does the graph of this thing look like? It goes like this, here,
And the same thing.
then it's over here. So is this one odd or even? Even. Got y-axis symmetry now. Now watch this. What's the limit as x approaches 0 of this function?
Infinity.
It is infinity. It's not that it doesn't exist. Yes, infinity doesn't exist. We don't know how big infinity is, but they're both going the same direction. So it does settle from the left and the right on the same number,
Which happens to be infinity.
which is not a number. But it settles on the same thing.
And so that's the limit.
That's the limit. And here's what we say. The limit as x approaches 0 from the right of f is infinity. The limit as x approaches 0 from the left of f is that same entity, whatever it is. Therefore, the limit as x approaches 0 is that same thing. Even if the thing that it's approaching is undefinable. As long as it's the same undefinable thing.
So there's like, I know we're not working with imaginary numbers, but if it was an imaginary number, it still would be?
Yep. So since these are both going up as you go to 0, the limit does exist at 0 from the right and the left because it's heading towards the same thing. This one doesn't because it's heading in different directions. One's going up, one's going down. See the difference? These are all very subtle, interesting things. Look at example 5. Considering the same idea, it says the graph of f equals tangent x, which is sine over cosine, has infinitely many vertical asymptotes. You knew that. There's a picture of it to the left there. You've seen that before. One at each point where the cosine is 0. If a, it's constant, if a is an odd multiple of pi halves, then the limit as you approach a from the right of any of those asymptotes, as you approach that asymptote from the right is negative infinity, and the limit as you approach that same thing from the left is positive infinity, suggesting those limits don't exist there. But there's a whole bunch of vertical asymptotes now. Every constant that is an odd multiple of pi halves. We good? Or not really? I know you guys are trying to fight a fly. I don't know what that is. Now we're going back to limits as we go to infinity. So now we're going back to letting x be large. Or x large. Did you get it?
No. Those things, as soon as you start swinging, then you
Okay, I'm asking you to switch gears conceptually again. We're going to start letting limits go to infinity again, which means x's are getting really big right and left. Instead of approaching a particular x and letting the y's go big, we're approaching a very large x and figuring out what happens to y. We're going back to that. So I want you to consider this polynomial. 3x to the 4th minus 2x cubed
Well, that just big.
2x cubed plus 3x squared minus 5x. What's the last one? Plus 6?
Yeah.
No, I don't want to do it all over. I just want to just consider that one polynomial. I'm on example 6 at the bottom of page 73. Okay, and it says, let f be this polynomial and let g be 3x to the 4th. Show that while f and g are quite different numerically for small values of x, then they are virtually identical for large values of x. Here's how I want you to consider it. If we let x get fairly large, and we let x keep getting larger and larger to the right, do you understand that this term right here outruns these in a race? This one gets bigger faster than any of these others as x gets big. These are getting huge, but this is getting huger, faster, because it's to the 4th power. Do you understand this? So in the long run, these guys get left in the dust. They're sucking air, trying to even keep moving. This guy's way out in front of him, turns around, he can't even see him anymore after a while. And he's still running hard. These guys are still running pretty hard too, but they cannot keep up with him, and the gap keeps getting wider and wider and wider. So, under those conditions, the limit as x approaches infinity of g is this. Because these others contribute less and less and less and less to the value. Does that make any sense? Okay, let's see if we can apply it. What they've got there for you is a couple of graphs. Take a look. By the way, it's really important you understand how they put graphs together in this book. This graph right here, for example, I'll put it over here so you can see it. This graph right here on page 73. Notice that below it, it says it goes from -2 to 2 and from -5 to 20. Those are left side and right side and below and above. So these are just a shortcut way of writing x min, x max, y min, y max. You've seen that before, right? Notice that we've got the black one and the blue one, and that is, the black one is this one, the blue one is this one, and they are quite different when x isn't very big. But look at the next one down. It goes from -20 to 20, and from negative, looks like what, 100,000? 100,000 to 500,000? And this is a graph of both f and g, and you can't tell the difference anymore. Because as x gets really big, and it's really not that big yet, it's just out to 20. As x gets really big out to 20, this looks like this. You can't tell the difference because as x gets large, all the others become insignificant. Moving on. Well, let me show you something before I move on. If you take, we're going to call this new function that we settled on, this guy right here, we're going to call that f of x, so that we can refer to it easily. If you take g of x and divide it by f of x, here's what you get. 3x to the fourth minus 2x cubed plus 3x squared, 5x plus 6, all over 3x to the fourth. But as you know, if you have a monomial denominator, you can put it under each of them separately. Hang in there, folks. This verbal yawning is not acceptable. Let's simplify each one of these fractions. Shh. What does this one simplify to? 1. What does this one simplify to? 2 over 3x, right?
Yeah.
What is this one?
1 over x.
1 over x squared. This one?
5 over 3x cubed.
5 over 3x cubed. Yep, that's
And
it.
this one?
2 over x cubed. Yes.
Now what's the limit as x approaches 0 for each of these? What's the limit as x approaches 0? Not 0, infinity. What's the limit as x approaches infinity for this term? 1. This one?
Infinity. Negative infinity.
0.
0.
Oh, wait.
X is going to infinity.
Yeah, because it's 2 over 3.
2 over something getting larger and larger and larger. The whole value of that's getting smaller and smaller and smaller. In other words, this is the mathematical way of saying this thing's getting outrun by this one.
Just
So this is going to be 0. This is going to be 0, even worse. This is going to be 0. This is going to be 0. And so the limit is 1. If you divide the original function by what you believe it's settling on, if you take that divided by the function that you think it's approaching, because that's the biggest one, and you get 1, sorry, that's supposed to be a 1. If you get a 1 when you divide the original by what you believe it's settling on, that tells you that this is what we call an end behavior model. This thing you divided by is an end behavior model. End behavior means way the heck out there. This thing becomes this model at infinity. Why is that useful? You'll see in just a second. Yep.
So basically, if the first two terms are the same, it'll be like that model.
First 2 terms?
Like the first term on both of them is like the same.
No, here's what we're considering. Here's G. The question you're asking yourself is, as x gets large, what is that settling on? And you say, it's settling on this one because it's the outrunner. It's running everybody out. So you test it to see if you're right by taking the original function g and dividing it by what you suspect it's becoming and see if it settles on 1. If this original divided by what you suspect is its end behavior turns out, if the limit as x approaches infinity turns out to be 1, then your assumption was correct. And with polynomials, it's a really easy thing to come up with, but not all functions are polynomials. Still, this fact holds. If you have a strange-looking function here, and you think you know what it's going to become, what it resembles the most as it goes to the right, divide that weird-looking thing by what you suspect is its end behavior and take its limit of that quotient. If that limit turns out to be 1, the number 1, then your suspicion is correct. You see what I'm saying?
Yeah.
We're going to see that in a minute with some very strange functions. Yep.
Do you have any polynomial won't the leading term or the highest degree term be its end behavior model?
For polynomials.
Yeah.
Lots of functions aren't polynomials, but you're absolutely right.
So just find the first one.
Yeah, the end behavior model is the leading term. If it's a polynomial, if it's something else, this theorem still holds, which says this. If you take your strange function, you don't know what the limit is at infinity, but you suspect you know, take the original, divide it by your suspicion, take the limit of that quotient. If that limit is 1, then you are correct. This is the end behavior model. That's what we're saying. That's the theorem
So we suspected the end behavior is 3x to the 4th.
for this polynomial because it was an easy thing to analyze. Now we're going to analyze something that's not so easy. Okay, but using this theorem. The theorem is stated at the top of page 74. It says the function g is a right end behavior model for f if f over g's limit at infinity is 1. Or if its limit at negative infinity is 1. Has to be 1. Because they have to turn out to be the same thing. And a function over itself would be 1. So at the limit, they need to turn out to be the same thing. All right, so look at example 7. We're still dealing with polynomials here. Still dealing with polynomials. Shh. And then we'll go to this last example. We've got plenty of time. We'll go to this last example, example 8, and show you something that's a strange looking, weird, bizarre function and see if we can apply the theorem. So look at example 7. We have a 5th degree polynomial on top, a 2nd degree polynomial on the bottom, and we're dividing them by each other. What do you suppose the limit as x approaches infinity of f of x is?
2x cubed over 3.
Yeah, 2x to the 5th over 3x squared, which is really 2/3 x cubed when you simplify. Because the end behavior model for each of the polynomials, the numerator and denominator, is their leading term. So you put one leading term over the other leading term, simplify it, and you get 2/3 x cubed. That's going to be its end behavior model. That's what it's going to look like in the end. That quotient is going to look like in the end run. Did I lose you? Anybody? You lost? Totally? Oh boy. This isn't really an application of that theorem that I just said. What we're going to do is we're going to consider the limit of each polynomial separately, and then the limit of each one over the other is going to be the limit of the quotient. Let me say that slower.
Yeah, sorry.
Okay.
I was reading the problem.
Oh, okay. We got those two polynomials. One's in the numerator, one's in the denominator. If we consider each of their limits separately, like that property told us to do, this is one place where it's useful. If we consider the limit of the numerator, we know that it's going to, in the long run, as x gets really large, that thing's going to look like 2x to the 5th. The denominator is going to look like 2x squared. So the quotient of those two polynomials is going to look like 2x to the 5th over 3x squared. Well, if we simplify that and knock out as many x's as we can, we end up with the 2 over the 3, and we end up with 3 x's left.
So we're just looking at the beginning ones, really.
Yes, because the other ones are going to get outrun by the beginning ones. And so the beginning big guy over the numerator big guy over the denominator big one simplified is what that quotient, one over the other, that function, which is a polynomial over a polynomial, will look like this in the long run.
That's right.
As x goes to infinity, yeah. Okay? So what will g of x approach? The b part of example 7. 2/5. So that one actually has a horizontal asymptote of 2/5. That's what it's going to approach in the long run. It's going to actually get closer to the number 2/5, which is a horizontal asymptote there. This one's not going to approach. This thing's just going to keep getting bigger. But that second one, because the degree of the polynomials is the same, will approach the number 2/5 because all the x's get knocked out. What will this one approach if I have a polynomial? If I have a situation like this, if I have an h of x equals 3x squared plus 2x minus 1 over 4x to the 4th plus 3x minus 2. What will that one approach in the long run?
3/4 x squared.
It will approach this, right? 3x squared over 4x to the 4th. Isn't it? It's just the leading terms, right? This is a 4 here.
3 over 4 to the 4th x squared.
Equals 3 over 4x squared. What does that thing approach in the long run?
4x squared.
0.
Oh.
Denominator's getting big without bound while the numerator is stuck at 3. That entire fraction as x gets large is 0.
So then does h of x approach 0?
What's that?
Then does h of x approach 0?
Yes. So we say this, and looking at analyzing this, we say the limit as x approaches infinity for h is 0. You knew all of this from pre-calculus. It's just that now we have a reason to justify it. We said, if you have a polynomial over a polynomial, there will be a horizontal asymptote at 0 if the denominator's degree is less than the numerator's the numerator's degree is less than the denominator's degree. X equals 0 is a horizontal asymptote. Y equals 0 is a horizontal asymptote. Do you remember that?
Yeah.
This is why. This is why. Because our definition of a horizontal asymptote is a limit at infinity. And it goes to 0. You've seen it now. If the degree of the numerator is greater than the degree of the denominator, there won't be a horizontal asymptote because this thing gets bigger without bound. And if the degree of the numerator, as in the B part, is the same as the degree of the denominator, look to the leading coefficients. Y equals 2/5 will be your asymptote. These are why. Because we haven't considered limits before. We just gave you the facts and said, decide where the asymptote is going to be if there is one. Now you know why. But you knew this stuff before as far as a polynomial over a polynomial. Okay. So now we are going to look at this strange, bizarre function and try to apply the theorem. Let me remind you of the theorem. If you've got a strange function and you suspect you know the function it's going to approach, you put the original function over your suspicion and take its limit at infinity, and if you get 1, then you're correct. So here's our strange and bizarre function. Example 8. We have f of x equals x plus e to the negative x. That's probably not something that you got a good idea what that looks like. You could graph it, which is probably a good idea when you're actually doing this, to try to figure out what you suspect it will be. So graph this function. Tell me what you believe it resembles when x is really big. So you're going to have to look at the function way out there at a big X and ask yourself, what does that thing look like?
A big V.
Yeah, it's a big V. You're right. But as X gets really, really big, does it look like something you're familiar with?
Just your average X graph. How big are we thinking?
Just go out to 10. That should be enough. What does that thing tend to look like as you go farther and farther right?
Equals X.
Yeah. And doesn't that make good sense? Because look, as X gets larger, this thing, which is really 1 over e to the x, gets smaller. This thing's getting big pretty quick, and 1 over it's getting small, approaching 0 really fast. So really, in the long run, as x gets larger and larger and larger, this is getting smaller, 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 and this is getting bigger. So we end up with y equals x, because this contributes less and less and less as we go out. That's what I mean. Think about it rationally. So you suspect, and this is, if it says prove it, you suspect that g of x equals x is the end behavior model to the right. Right? That's what we suspect by analyzing this. This is going to 0. So we suspect that this whole thing is going to x. Oh crap, we don't have a lot of time. Here's how you do it. Just hang in there, hang in there. The limit as x goes to infinity of f, x plus e to the negative x, over x, that's our suspicion, is the same thing as the limit as x over x plus e to the negative x over x. This is going to 0 while this is getting huge. This is going to 1. QED. This suspicion as our end behavior model was correct, because its limit of the original function over our suspicion turned out to be 1. That's how you use it. Okay, that's enough for you to do this. Even though I didn't quite finish the section, you got plenty enough to move on with. Okay, so both of them are assigned. I will see you in a week. Get all of that work done that I gave you. All of this stuff right here. Can someone please give this to Kylie when you see her?
So lesson 2.1 and 2.2 also.
I was thinking,
You give it to Kylie for me?
oh wait, I don't have a copy.
What did you say?
Miss Jane, I'll just do one day.
I'm in a few of her classes.
Okay, that'd be great, thank you. Just put it in your backpack, give it to her when you see it, when you see her.